Okay, so we have a bobsled traveling around a turn. Now, at 67 miles an hour, if the radius of track is 20 meters, determine the angle of the embankment. So the angle of the embankment refers to this angle right here, the angle made between the horizontal and the track itself. As you can see from an above view, this box is your bobsled, and this is supposed to be a side view of the bobsled. Those those are supposed to be the blades. Here's the icy surface, and that's the bobsled itself and somebody's head. So that would be our object of interest. Um, since bobsled is done at the Winter Olympics on ice, we will assume that the surface is frictionless. So unlike a car traveling around the road, friction will not hold this sled down. It will just be the embankment of the turn that is pointing towards the center of that circle. So the center of the circle in this case will be somewhere in the horizontal plane of this bobsled. So our circular acceleration, our centrifugal acceleration, is pointing towards the center. Alright, now let's consider this what's interacting with this. If we look at this, we would have the Earth pulling down and the embankment pushing up perpendicular to the surface, our normal force. So we would have the Earth, and we'll just call it the track instead of the embankment, because then you have two E's and it just becomes confusing. Alright, so using the space below, here would be the bobsled. We have the Earth pulling down. Alright, that'd be the force of the Earth on the bobsled. And then we have the track, or the embankment, pushing perpendicular to the surface. So it's going to be a pretty drastic angle here. Now, if we kind of look at this from this perspective here, let's do a little trig which will help us out. Alright, so this here is theta. If I dot in my horizontal, okay, I also find that this is theta. If I dot in my vertical, this would be 90 minus theta, which would make this over here theta. So in this picture, I'm going to label my angle theta as this over here. So this would be the force of the track on the bobsled, and then this would be the acceleration pointing towards the center. Alright, now if we look at this, going to have to use components. So we're going to have the force of the track that's exerted straight up. This would be the force of the track. Oops. The force exerted by the track on the bobsled times cosine of our unknown angle, and pushing across would be the force of the track on the bobsled times sine of our unknown angle. Okay, acceleration is pointing towards the center. Now we can set up Newton's second law in the x direction and in the y direction. So in the x direction, we have our circular acceleration is equal to force of the track times sine of our unknown angle divided by our mass. In the y direction, we have 0, since it's only accelerating across towards the center of the turn. This would be the force of the track times cosine of theta minus mg. Alright, we need to find the angle here. We're given the speed, and we're given the radius, so we'll substitute in v squared over r is equal to the force of the track times sine of theta, all divided by the mass. We aren't given the mass, so we're going to have to make some substitutions here to see if it will divide out. If I solve for the force of the track, because it's going to be the same in both cases, I have the force of the track times cosine of theta is equal to mg. If I solve for the force of the track, I divide both sides by cosine of theta, which would be mg divided by cosine of theta. If this looks familiar, it should we did something very similar in the last problem. So now I have the force of the track. I can substitute this in. I would then have v squared over r is equal to mg divided by cosine of theta times sine of theta divided by m. M's divided out. Sine over cosine is tangent. So we have g tangent of theta is equal to v squared over r. Well, I need to find what theta is, so I can isolate tangent of theta. I have then v squared over g times r is equal to tangent of theta. And then theta itself would be the inverse tangent of v squared divided by gr. If you calculate this out, this works out to be about 87 degrees. Alright, very steep turn, but that's because they're going insanely fast.